and welcome class to part 2 of chapter 16, where we are building off, obviously, of part 1's discussion of the basics of equilibrium expressions and reversible reactions. In this part, it's not even that part 2 is entirely separate from part 1. I very well could have combined this lecture with the previous one, but there is a slightly different flavor to this lecture, where previously we were just kind of laying down the basic groundwork, definitions, the foundation, right? And here we're building off of that foundation a little bit in the sense that we're going to be learning how to manipulate these equilibrium expressions. So it's really important to recognize that the reactions, again, that these equilibrium expressions correspond to are reversible. And so all of our previous discussions for reactions, to a degree, can still apply here. We can still add up chemical reactions, like how we saw with Hess's law. Because these reactions are truly reversible, we can flip them around, so reactants become products, products become reactants. But each of these manipulations to the reaction as it's written is also going to have an impact on the equilibrium expression. So that's going to be what we are going to be talking about in this part of our Chapter 16 lecture. All right, and before I forget, I also want to mention that the rest of this lecture, the bulk of the lecture itself, again, is a modified version from last spring. So, keep that in mind moving forward. A number of the lectures continuing for the rest of the semester will be modified versions from the previous spring's lecture series. And that's perfectly fine. So, just kind of be aware of that. I don't want to, keep making this announcement before every single one of my lectures. So I think 3 times is enough. Moving forward, if you notice that the audio quality is slightly different than what you've been used to, that's going to be why. Okay, so equilibrium constants, now that we've kind of started tying them to numbers, quantitatively speaking, can also be manipulated. So reversible reactions, much like complete reactions, can be added together, they can be written in reverse, they can be scaled up, they can be scaled down. And so what we're going to be doing now is looking at how does the equilibrium constant, which gives us information about that reversible reaction, how is it affected by these types of manipulations that we can make. So the first example we're going to look at is what happens when you write a reversible reaction in reverse. Since a reversible reaction can meaningfully be written in reverse, right, this is telling us, this first situation is telling us the exact same thing as this second situation, that we're working with a reversible reaction, and that N2O4 is turning into NO2. Only in the second case now we're saying, oh, 2 NO2s can be synthesized to make N2O4, but that's the exact same thing as when our first reaction goes in reverse. However, for, again, consistency's sake, we're always going to be looking at whatever is on the left is the reactant, and whatever is on the right is going to be the product. And since your equilibrium constant is always going to be a ratio of product to reactant, in reversing our chemical equation, this is also going to change how we see our equilibrium constant. So the equilibrium constant for the first situation, our K sub capital C, is we found was equal to 4.65 times 10 to the negative 3. Well, if we reverse the reaction, our new Kc, which is going to be equal to the concentration of our product, which is the N2O4, divided by the concentration of our NO2 squared, we can see here that this expression is the exact inverse from what the first reaction was, right? We calculated our first Kc because our concentration of NO2 squared was divided by the concentration of N2O4. These two things, these two expressions, are the exact inverse of one another. So in other words, if you have a reaction that is written in one given direction, like our N2O4 decomposing into 2 NO2s, if you reverse this reaction, what's going to happen to its equilibrium constant is that your new equilibrium constant will be equal to 1 over your old equilibrium constant. So our new equilibrium constant is going to be equal to 1 divided by 4.65 times 10 to the negative third, and this is going to give us a value that is equal to 215. Now, regardless as to whether or not this reaction is written in the forwards direction or is written in the reverse direction, this is going to, the two values that we have here are going to tell us a little bit of something about or a little bit of information about the reaction. The first situation, the first reaction, as it's written, we see that we have a smaller equilibrium constant than if it's written in the other direction. What this is telling us is that the ratio of, in the second situation, our product, is greater than the concentration of our reactant. The reason why we can draw that conclusion is that our value here, 215, is definitely larger than 4.65 times 10 to the negative 3. This is a value that is greater than the ratio of 1, meaning that you're going to, numerically speaking, have more product as your reaction is written than reactant. In other words, you're going to have more N2O4 than what you have NO2, regardless as to how you write this reaction. Or another way that we can manipulate these chemical equations is if we write a reaction that is the sum of like two types of constituent reactions. So if we take our first reaction here, which is the, again, same reaction that we've been working with, our N2O4 is decomposing into two NO2s. Its equilibrium constant, as we have seen, was 4.65 times 10 to the negative third. The second type of reaction is another reaction that's been demonstrated to be in some type of dynamic equilibrium, reactants and products, kind of all existing in one beaker, one pot. The two NO2s are going to be, in this case, decomposing and reacting to create two nitrogen monoxides as well as an oxygen gas. The exponent on its equilibrium constant is very small, meaning that this reaction definitely favors reactants. Again, because in the way that we write products divided by reactants, this very small number means that we have a very large denominator, meaning that we have a very large number of reactants. Needless to say, though, or regardless of that point, this is still a reaction that exists in equilibrium. If we want to figure out what the equilibrium constant would be for this third given reaction, well, all we have to do is look at what the two previous equilibrium reactions were telling us, because this third reaction is actually just the sum of reactions 1 and 2. Right, so if we add reaction 1, all of its reactants together, and add all of the products together, the two NO2s end up canceling out when adding everything together, and we are only left with this N2O4 on the reactant side, our two nitrogen monoxides, and our oxygen gas. So this is another way that we can write sort of like the combination of these two previous dynamic equilibriums. Well, if we want to know then what is the equilibrium constant representing this new equation, let's figure out what we have to do, like to the two previous equilibrium constants. What do we do to Kc1? What do we do to Kc2 in order to figure out what this equilibrium constant is? In other words, what is the dynamic nature of this third reversible reaction? Okay, so how to find this? Well, let's kind of ignore this top information. Let's just write out what is our equilibrium expression going to be equal to? Well, we have a ratio of products, our first product being this nitrogen monoxide, and we're going to square the concentration of that value since there is an exponent of 2 here. We can multiply that by the concentration of O2 gas and divide it by the concentration of our other, or of our reactant, the N2O4, the other chemical species here. Well, what we can see here is this is actually a combination of the previous two equilibria. In other words, this is equal to our first equilibria, where this product here divided by the reactant, right, dividing by the reactant, which is now down below, NO2 squared divided by N2O4, multiplied by the second reaction's dynamic equilibria, right? The nitrogen monoxide is present here, nitrogen monoxide, our oxygen gas also being in the numerator, all divided by this NO2 squared. There's a squared there. If we follow the rules of algebra then, if we take a one fraction multiplied by another fraction, what we're really doing is multiplying the numerators and multiplying the denominators, but keeping this line kind of steady in between. What this means is that our NO2 squared concentrations are going to cancel out, leaving us exactly with the equilibrium constant that we just determined when looking at the reaction that we are working with itself. In other words, the equilibrium constant, as we can write out using our concentrations, is simply equal to the multiple of the equilibrium expressions from the first two reactions. Our Kc prime is equal to Kc1 times the value of our equilibrium constant for Kc2. So if we want to find Kc prime numerically speaking, and we don't have any types of concentrations around, all we have to do is look at the equilibrium constants for these first two reactions and multiply them together to figure out what this Kc prime is going to be equal to. Now what this value ends up being equal to, if we take a 4.65 times 10 to the negative third and multiply it by 1.63 times 10 to the negative 10, what we are left with is a value that is 7.86 times 10 to the negative 13th. The combination of these two reactions then, the first reaction and our second reaction, is going to leave us in a situation where we now have this new dynamic equilibrium that is going to be, at least we can tell by the number here, our equilibrium constant, heavily favoring the existence of our reactant. This N2O4 is going to be the most stable species, since according to the ratio of its products to reactant, we're going to have a very large denominator, a very large reactant concentration. Okay, the last way that we can manipulate these equilibrium constant expressions that we are going to be introducing here is that they can be scaled up and scaled down. So again, we're going to be looking at this N2O4 expression reacting reversibly with the NO2. If we scale up this reaction, in other words, there was previously a stoichiometric coefficient of 1, now we have doubled it. Similarly, there were 2 NO2s, now we have doubled that, we have 4 NO2s. Our equilibrium expression we can write out again from the equation that we have listed here, and that's going to give us some information about how we can use the first equilibrium constant, this known, to figure out what this unknown is going to be. Because really that's what we've been doing this entire time so far. When discussing the manipulation of these equilibrium constants, we have simply been looking at, okay, you have a reaction with a known equilibrium constant. How can you use that to figure out the equilibrium constant from this manipulated version of it? Either you've been scaling it up or reversing it or adding it to something else. What does it mean in terms of the dynamic equilibrium, and what does that value tell us? So, if we scale up our reaction, our equilibrium constant we can write out again as a ratio of products to reactants. And if you're getting tired of hearing me say ratio of products to reactants, boy do I have some news for you, because we are going to be using that phrase a lot. So the equilibrium expression, our Kc prime, is going to be equal to the concentration of our NO2 to the fourth, all divided by the concentration of the NO2 or N2O4 to the second. Well, this is the exact same thing as taking our first equilibrium expression, the NO2 squared, all divided by the concentration of N2O4, and squaring it. Right, we now have an exponent of 4 in the numerator and an exponent of 2 in the denominator. This is the exact same thing as if we squared the first equilibrium constant we had. In other words, we are squaring the value of Kc to find this new Kc prime. And so your Kc prime, numerically speaking, is going to be equal to 4.65 times 10 to the negative third squared. So if we double a reaction, we're going to take that factor and raise it up into the exponent of our old Kc to figure out what the new Kc is equal to. This is going to give us a value that is equal to 2.16 times 10 to the negative fifth. All right, so we can see in doubling our reaction, the equilibrium value here has actually shifted a little bit more towards the reactants, that the value of the concentration of our reactant now is going to be a little bit greater since the value of our equilibrium constant has gotten smaller. And I hope that this conversation of the relative values of reactants to products so far has been somewhat meaningful. I realize that, again, there's no dynamic conversation between you and I. So if there are any questions, I mean, absolutely, I hope you are writing it down. I hope to get a number of questions as this week progresses, so that way we can clear up any misunderstandings. But before moving forward, let's kind of recap these 3 different forms of manipulation and what, I guess in one kind of sentence, how we can describe them. So if you are writing your reactions, your reversible reactions in reverse, you're going to invert Kc to find Kc prime. That's basically what we did. We wrote our reaction in reverse between steps 1 and 2, and so to find our Kc prime, all we did was take the inverse of our first Kc. And this is going to be true no matter what type of reversible reaction you are working with, because this math of taking the inverse of your concentrations of products and reactants will always be true. So this is sort of our step 1. Our second manipulation was taking a reversible reaction and adding it to another reversible reaction. If we do this, then we are going to multiply their Kcs, which is exactly what we saw here. And the reason why, again, we saw as the math worked out, as we lay out for this new Kc prime what the ratio of products to reactants is, we saw that it was exactly the multiple of the previous equilibrium constants for the previous reactions that were added together. Again, this is always going to be true no matter what type of equilibrium you are working with. If you add two reactions together that are reversible, you will multiply their equilibrium constants to find the new equilibrium constant for the new reaction that results from the two previous being added together. And 3, if your reversible reaction is being scaled up or scaled down in some way, you are going to, raise that constant multiple into the exponent of Kc, which is exactly also, again, what we saw here. We scaled up our reaction by 2, and we see that the Kc was squared. So if we, let's say, instead increase or scale up our reaction by 3, we would actually have a 3 in the exponent here. If we scale it up by 4, we would have a 4 in the exponent. If we scale it up by 1/2, let's say, we would have 1/2 in the exponent here. You see where I'm going with this? So this is the recap then of the 3 previous rules, kind of in like one sentence instructions. How is it if you are manipulating your equilibrium expression, you can manipulate, or if you are manipulating your reversible reaction, rather, this is how you manipulate its equilibrium expression or equilibrium constant to give you new information about your new manipulated system. Okay, so the last topic that we're going to be talking about before I let everyone go before this lecture is finished, is the equilibrium of ideal gases. So I did say previously when discussing homogeneous versus heterogeneous and how do we know which values we're going to be putting into our equilibrium expression, the idea was that we want a species that has a variable concentration. That way, as the reaction progresses and the concentration is changing, we can actually figure out when do we hit this equilibrium where the concentration is no longer changing. And the 2 species that we are going to be including are species in an aqueous form and species in a gaseous form. Well, you can record a concentration of a gas, right, moles per liter, since the value of the number of moles and liters can be different. But we also know with ideal gases, this concept of concentration is actually proportional to pressure. And so for this reason, we can figure out or record an equilibrium constant for gases using their pressures as well as their concentrations. So both gases and solutions have variable concentrations, exactly what I was explaining here. And the partial pressure of your gas is going to be directly proportional to the concentration, which is what I've outlined here. So, since the concentration is proportional to pressure, instead of inserting concentrations into your equilibrium expression, if your equilibrium expression has a base of P, in other words, if it's dependent or based on pressure, your values that you're going to be inserting, your products and your reactants, are not going to be concentrations, but they will be partial pressures. And so the exponents we can see are going to be those stoichiometric coefficients still, but instead of inserting concentrations with that bracket notation, meaning pressure or a concentration of, we now have partial pressures, which is a big P, with a sub of your species. So this would be partial pressure of A, partial pressure of B in the denominator, partial pressure of C, and partial pressure of D in the numerator. So we're still looking at products divided by reactants, it's just now we're working with partial pressures instead of concentrations. Okay, so does this mean, though, that the value of your K is going to be the same? Well, to that, I would ask you another question in response, which is your concentration numerically equal to your partial pressure? And the answer there is no. You're working with completely different units, completely different concepts, and so Kp is not going to be equal to Kc. They're actually going to be equal to two different values. So if you're recording partial pressures or if you're recording concentrations, you're going to have to be careful about what type of equilibrium you are working with, and make sure that you're keeping your subscripts, your C's and your P's, consistent. All right, but we can relate Kp and Kc to one another using the ideal gas law. So we can convert between Kc and Kp using this equation here. So your Kp is going to be with pressures. Your Kc is going to be with concentrations. The way that we can convert between these two then is by taking into account mathematically the ideal gas constant, which is your R, your temperature, which has to be in units of Kelvin, your ideal gas constant in this form, since we are working with the ideal gas law equation, is going to be the 0.08206 liters atmospheres per mole Kelvin. And your delta N, this is a new piece. So what does your delta N equal? Your delta N is going to be equal to the change in number of moles from, well, reactant to product. In other words, we're going to be taking a final minus initial, product minus reactant, molar kind of calculation. And if we aren't given explicit values of moles, we're going to be using our stoichiometric coefficients out in front of our gaseous species to figure it out. Okay, so let's see an example of this equation in action. Let's see what the Kp of the equation that we have been working with is equal to just at room temperature, so 298 Kelvin. All right, so definitely take a break from the video, try this math for yourself. We have the Kc, it's the same Kc that we have been working with. We have the ideal gas constant, we have temperature. So try this calculation for yourself before moving on. But I am going to continue moving on. Our Kp is going to be equal to our Kc, which is 4.65 times 10 to the negative third. Our gas constant R is going to be 0.08206 liter atmosphere per mole Kelvin. Our temperature is 298 Kelvin, and we're going to raise all of this up into the delta N. And so we're looking at the change in moles from reactant to product. But what we are going to be, like how we're actually going to be using these numbers is just like before. We're always going to be looking at a final minus initial type of number. So number of final moles or product moles, and we're going to subtract out the number of initial moles or the number of reactant moles. So this delta N for our provided reaction, since we're looking at a gaseous species here and a gaseous species here, we're looking at the change in the number of gaseous moles, not just moles in general, but it has to be gaseous moles, is going to be 2 minus 1, right? We have 2 moles of product minus 1 mole of reactant, 2 minus 1 here. All right. So the exponent is going to end up just being a 1, so we're basically just multiplying each of these terms in this situation. This exponent, though, will not always be equal to 1. Sometimes it will even be a negative number, and that's totally okay. Sometimes it'll be 0, and that's also okay. But we need to be paying attention to what the numbers of moles here are equal to figure out how this equation is going to work out. So our Kp for this expression, for this N2O4 breaking down into 2 nitrogen dioxides, is going to end up being equal to 0.114. And the difference in these two values then, one being 4 thousandths and the other one being 1/10th, completely has to do with what our perspective is, what our units are in pressure versus concentration. Okay, so here we have an example problem that I definitely, again, suggest you kind of pause, see if you can't figure it out. This is a problem that is based on the previous example that we just worked through, the, interchangeability between Kc and Kp. So the calcium carbonate species in this reaction below we can see is breaking down into calcium oxide and carbon dioxide. This is going to be kind of a combination problem, actually, between all of the concepts we've been talking about today so far, tying them all together. See if we can't draw some information about this chemical equation, about this decomposition, and how much carbon dioxide we'll actually get on the other side. So calcium carbonate is known to decompose at high temperatures. If the partial pressure of carbon dioxide at the end of the reaction is found to be 3.65 atmospheres, and we are, again, working at high temperatures, so something like 1188 Kelvin, what is the Kp and the Kc for this reversible reaction? Okay, so let's look at it, in my opinion, a very fun example. So it's fun because there's a very nice trick to it. You might be thinking, like, I don't have any values for calcium oxide or calcium carbonate. How am I supposed to figure out what my Kc or Kp is equal to if I don't have any type of, like, information aside from the pressure of the carbon dioxide? Well, our Kc and our Kp expressions, let's just write out both of them, observing our reactants and products, and maybe that'll give us a clue as to how we're supposed to progress in this problem. Well, when writing out our Kcs and our Kps, we learned back when it came to heterogeneous equilibria, which is exactly what we're working with, that if all of our species are not in the same phase, we are only going to include aqueous and gaseous species. We do not include liquids and solids. So even though in the wording of this problem we don't have any information for calcium carbonate or calcium oxide, we actually don't need it. These species, since they're solids, we don't include them in our equilibrium expression. Our Kc will end up being equal to the concentration of carbon dioxide. There's no coefficient in front of it, so this is it. Our Kc is equal to concentration of CO2. Similarly, our Kp is equal to the partial pressure of CO2. The other species don't apply. They don't matter. So our equilibrium is going to be solely dictated by the ratio of carbon dioxide to 1. If you have no reactant, if you have no additional product, there's sort of like a 1 as a placeholder there, and any number divided by 1 is itself. So we're just looking at concentration of CO2 or partial pressure of CO2. And so from here, we can now observe the, again, wording of the problem, see if we don't have any information that's going to be useful to us based on either one of these two equations. And yeah, we have a partial pressure of carbon dioxide right here. The Kp is going to be equal to the partial pressure of your carbon dioxide, which is 3.65 atmospheres. And that's it. This 3.65 is going to be equal to your Kp. First problem solved. Now, we also just learned an equation to figure out Kc from your Kp, right? The equation that was Kp is equal to Kc times RT, all to the delta N. So the values that we have so far, we have this 3.63 that we can insert in for our Kp, or 3.65 inserted for our Kp. I just instinctually want everything to rhyme. This is going to be equal to our Kc multiplied by our value of R, which is our ideal gas constant, 0.08206 units of liter atmosphere per mole Kelvin. And I'm going to bracket this off since it's the gas constant times R. That's all raised up to the delta N, so it's going to be very important to keep this information together. Our temperature is at 1188 Kelvin, and we're going to raise all of this up to the delta N. Now again, the delta N is only going to apply to gaseous species. And so if we observe again our chemical equation, we have a solid, so it doesn't matter. This coefficient of a 1 doesn't get included. We have a solid, this also doesn't matter. This coefficient of 1 doesn't get included. We only have one gaseous species. So if we're looking at moles of product minus moles of reactant, we have 1 mole of gas as a product and 0 moles of gas as a reactant. So our exponent here is going to be that 1 mole of product minus the 0 moles of reactant. And now we have a way to rearrange algebraically and solve for what our Kc is equal to, and our Kc is going to be equal to 0.374. So now we have a value for our Kp. So if we wanted to continue working with this problem from the perspective of partial pressures and gases, we could. If we wanted to continue working with this problem from the perspective of concentrations, we could also do that. We have found all of this equilibrium information just from one partial pressure, as well as knowing what the temperature of the equilibrium or reversible reaction, what it was occurring at. And with that, we are going to call this a lecture. So between parts 1 and parts 2, we have a pretty good idea, thus far in chapter 16, for how equilibrium constants work, how they can be viewed, how they can be manipulated. But what's really important to note is thus far we've really only been focusing at equilibrium conditions. So the reaction has reached an equilibrium state, the forward and reverse reaction rates have become equal. What we're going to begin exploring then for the rest of this chapter is, what if that's not the case? What if we've just mixed our reactants? Or what if we reached equilibrium but then, oh no, we accidentally spilled in some extra reactant? Like, how's that going to affect things? So of course this conversation is going to be a little bit more difficult, but that's why we break it down into these different parts. So in part 3, we're going to be looking then at starting from initial conditions and seeing how we can use the equilibrium constant to predict which way the reaction is going to go. So if you have any questions, as always, please do not hesitate to ask those questions. And if you have homework, do your homework. Until next time, class is dismissed.